Hey, Chem Coach Powers here, and we've got another lecture for you because you love chemistry. Hopefully, you're getting to love it as much as I do because chemistry is awesome. All right, so today we're going to be talking about some pretty cool things. We're going to be talking about polarity. Okay, we've talked a little bit about bond polarity. Now we're going to amp that up to talk about molecular polarity, and that's going to connect us to some really cool concepts. And then we're going to talk about a couple different types of forces, like London dispersion forces, hydrogen bonding, dipole-dipole bonding. We've got these various different types of intermolecular forces that we want to talk about. These forces are really critical for life and pretty much anything. But life, your DNA is held together by certain types of intermolecular forces. We're going to talk about some of that stuff today. Got a lot of objectives, got a lot to do, so let's get going. We want to use molecular shape and electronegativity to predict our molecular polarity, to figure out what's the difference and articulate with our words the difference between intermolecular attractions and interatomic forces. Notice I have in parentheses bonds here. Intermolecular attractions are different than bonds. Describe the three main types of intermolecular forces. We've got dipole-dipole, London dispersion, and hydrogen bonds, and their different strengths. And describe how IMFs, intermolecular forces, are going to affect things like boiling and melting points. It's pretty neat stuff. All right, so your criteria for success. You can explain the influence of bond polarity and molecular shape on the polarity of a molecule, and that's going to help you describe properties. Again, we love how this stuff connects to properties. Given the formula for a molecule, you can draw its fluid structure, predict its shape, and determine whether or not it is a polar molecule. Given a molecular formula, you can predict the type of intermolecular forces it will have. And given formulas for multiple molecules, you'll be able to rank them in terms of their increasing boiling points. Oh my goodness, you guys are going to be like geniuses by the time you're done with this lecture. All right, our molecular polarity. First of all, why are we looking at molecular polarity? Because the molecule's shape is going to affect its properties. And one of the biggest, most important properties of a molecule is its polarity. How many times have we, looked at something like oil and water and said, hey, why do oil and water not mix? And so many times as you guys grew up, you learned and heard and said that oil and water don't mix because of density. Wrong, okay? Nothing to do with density. Yes, they have different densities, but that's not why they don't mix. Why they don't mix has to do with polarity. Polarity has to do with so much in your life that you don't realize. It is why you are washing your hands to try to get rid of viruses and things like that. Why you need to use soap instead of just washing with plain water. Okay, we'll talk about that a little bit. What is molecular polarity? It's the uneven distribution of electrons within a molecule. So this molecule up here has more electrons around this atom than it does around this atom. When you have that uneven distribution of molecules, okay, you're going to have a side that's partially negative and a side that's partially positive. That is a polar molecule. So we need to get to the point where we can talk about and identify and describe a polar molecule. Okay, this is going to tell us how sticky the molecule is, and this is going to relate to things like boiling point and surface tension. And one of my favorite subjects to not talk about is the question, is water wet? It has everything to do with polarity. I've got a series of 7 TikTok videos that you need to watch if you like that question. I love the question. I just don't like the answer that most people give because most people are dumb. Okay, sorry. Did I just say that out loud? All right. Molecular polarity is determined by what? And not really that they're dumb, but just that they're dumb about that thing. Until I educate them. All right, molecular geometry, we have to do a symmetry test or a line test, okay? So 2 things that molecular polarity is determined by. It's the molecular geometry and the bond polarity. To do a little test on our geometry of our molecule, we're going to make a little line test and see the symmetry there. If the molecules are symmetrical from any angle, okay, then we would say, hey, you're not polar. If they are not symmetrical, then we'd say, hey, you are polar. And then the other part has to do with the bond polarity. If I have one atom that has a higher electronegativity than the other atom, and so it's attracting those electrons and pulling those electrons toward itself, then I'm going to have a dipole. When you think of dipole, I want you to think about like poles of a magnet, the south and the north pole, right? And they're different from each other. Same kind of thing. I have an electron-rich and an electron-poor region, a slightly negative part and a slightly positive part. And so I have a dipole. Okay, electronegativity difference of 0.3 or above is going to give you a bond polarity. And so then you're going to have a chance of having a molecule that's polar. But again, it has to do with both of these things, not just one, both of those things. Usually, if the two atoms are in a bond are different, then the bond is going to be polar. Okay, so for example, H and Cl, they are different. That's going to be a polar bond. But if I have Cl and Cl, they are not different. That's going to be a nonpolar bond. Okay, so bond polarity, though, that's different than molecular polarity. Let's talk about the molecular polarity here. As we look at our carbon dioxide, and we're going to apply the symmetry test to carbon dioxide and water and see how that pans out. Okay, so for our symmetry test, you can kind of see if I draw, there's a little line down this way, not very straight line, and down that way. A little line here, a little line here. Now, do I have the same thing in these quadrants? Oh, not in that one for sure, right? And so if I can apply the symmetry test and it passes the symmetry test, then I can say, hey, you are non-polar. And if it does not pass the symmetry test, I can say, hey, you are polar. Got it? That's a symmetry test. Just be able to draw a line. But again, you have to make sure that you understand the three-dimensional shape there, because that three-dimensional shape, remember, is not exactly the same as a two-dimensional shape. In this case, for instance, I can look at this and I can divide it in any way, and I've got 4 different atoms that are exactly the same, pulling exactly the same bond angles. This is a nonpolar molecule. However, if I were to attach a different atom on there, like a chlorine, instead of a hydrogen, this becomes a polar molecule, because this does not pull with the same intensity that a hydrogen does, right? And so these hydrogens are not pulling the same as the chlorine. The chlorine pulls the electrons more toward itself, so this becomes a polar molecule. Whereas this one is a nonpolar molecule, okay? All right, so that symmetry line test is a good one, but you know, it also helps to think in 3 dimensions, so try to do that. Okay, determine whether or not each of these are polar or non-polar. Make sure you do the Lewis structure first, figure out the shape, and then we go from there. All right, so let's pause and practice and come back in just a second. Make sure you do it. And you're back, right? You did your CH4. I just showed you that one. And so here we have CH4. And, you know, I might guess one way or the other in 2 dimensions, but in 3 dimensions, I now have a picture of it, and I realize, oh, each of those hydrogens is pulling exactly equal, and so that has got to be a nonpolar molecule, okay? If I were thinking in 2 dimensions, I might come up with a different answer. S, with its 2 H's, this is going to be a lot like water. The question is, do the oxygens pull with the same intensity that the hydrogens do? I say oxygens here. Do the electrons pull, the unpaired electrons, do they pull with the same intensity as the hydrogens? No, they don't. So again, if we think in 3 dimensions, let's just pop 2 of those hydrogens off of our carbon. If it would be as if we did this with sulfur, these actual hydrogen atoms are pulling because they have protons, so they're pulling at the electrons. There are no protons pulling at those electrons. Therefore, this is going to be a polar molecule. It's not even. It doesn't pass a symmetry test. Okay, nope, definitely not the symmetry test, right? Okay, and then CS2. What did you come up with CS2? Were you genius? Were you genius? Did you figure it out? This is very much like CO2, right? Oxygen and sulfur both are in the same column, so they have the same basic shape. So does that pass the polarity test? Okay, does it pass a symmetry test? In this case, it would be having 1 carbon, and then let's just go ahead and let's make a CO2 so you can see what that looks like. And you'll see it passing the symmetry test. This one is passing the symmetry test, and so this is going to be a non-polar molecule. All right, got to show you though, right? All right, so we get, there's one, and then if we attach this other one, then we get to see carbon dioxide. Same thing would happen with the carbon disulfide. You end up having a single line, okay? So it passes the symmetry test, even though you kind of be like, "Whoa, look at the lines, they don't look the same." But remember, these are electrons that are all zipping around anyway, right? So it passes that symmetry test. It's at a 180-degree bonding angle. They're both pulling, because they're equal, they're both pulling equally in exactly the opposite directions. A lot of times it's fun to think about a rope and multiple people pulling on that rope and pulling evenly. Like if these two people are exactly pulling evenly, then that person that's right in the middle stuck on the rope doesn't go anywhere, right? It's kind of fun to think about it in terms of that. Okay, so let's move on. Let's talk about our, well, and then we've got a couple of these. You can practice some of these if you want. I'm not going to go over these right now. We can go over them in class if you'd like. I want to go on. We've got a lot to cover, so I can come back to these if I want later, or you can talk to me about those later. All right, so let's talk about intermolecular forces, IMFs. And these are the forces that are forces of attraction between molecules. So for instance, if I had two different molecules, or maybe even if they were the same molecules, you know, I had a methane and another methane, if we were doing that. If you have two molecules, what kind of force of attraction exists between those two molecules? That's the kind of thing that we're asking about when we talk about intermolecular forces. It's the forces of attraction that exist between molecules, okay? So let's just assume I've got two little methanes. Okay, now this is a bond, okay? It's the attraction between this atom and that atom, and it's the actual chemical bond where they're sharing the electrons. But the intermolecular force, the IMF, has to do with whether or not this one is attracted to this one. It's the force inter or between the molecules, okay? Is there an attraction there? That's the intermolecular force that we're talking about, okay? For instance, what attracts one water molecule to a nearby water molecule? Remember that these intermolecular forces are always going to be weaker than bonds, actual chemical bonds like ionic or covalent bonds, okay? They're attractions, but they're not the same as bonds. Now, we can break hydrogen bonds and break these IMFs, we can break these intermolecular forces, and we have not changed the chemical. A lot of times, this breaking of these types of intermolecular forces is what gives us phase changes. But it's not giving us a new chemical, okay? So bonds, that's something different. That's a strong attraction where they're staying fixed in position. This is not going to be the same thing. All right, so remember that these intermolecular forces are going to determine things like boiling points, melting points, things like that. And the stronger the intermolecular force, the higher the boiling point is going to be. Let's talk about London dispersion forces first. Now, we're going to talk about them in terms of the weakest one, and then we're going to get to the middle one, and then we're going to get to the strongest one. The weakest one is the London dispersion force, LDF, and sometimes you're going to hear this referred to as an induced dipole attraction, okay? It's also called the van der Waals forces. Depends on the textbook that you get. Lots of different names for this. But this is the weakest of our interactions between these different molecules, but it exists between all molecules. And then the reason it exists between all molecules is because electrons are always zipping around. And this particular force has to do with electrons zipping around and moving around in random ways, okay? It's due to the temporary uneven electron distribution as the electrons continually move. And remember, the more electrons that you get, the more that intermolecular force becomes. So more electrons means bigger LDF, but it's still the weakest of the forces. But remember, this force is present everywhere, polar, non-polar. It's present in all molecules that are interacting with each other, okay? If you have a non-polar molecule, this is the only force that is existent between those. So here was our two methanes. We already said that methane was non-polar. The only interaction, the only attraction between these two molecules is a London dispersion force. an induced dipole. That's the only way these guys are attracted to each other. And they're not very attracted to each other, which is why this is a gas at such low temperatures. Okay, carbon dioxide, same thing, a nonpolar molecule. The only thing that is at work intermolecularly between one carbon dioxide and another carbon dioxide is London dispersion forces. It's the weakest of the attractions. It is not going to allow it to stick together at high temperatures. It boils away, or carbon dioxide, dry ice, right? It's going to sublimate away at really low temperatures. Okay, so let's talk about induced dipole attraction, just another way of talking about London dispersion forces, right? It's the attraction between an induced dipole and an induced dipole. You're like, induced dipole? What are you talking about, Powers? An induced dipole is where I can take and give you just a little bit of random chance, and all of a sudden you're going to induce a random chance dipole in another atom. Okay, we're going to show you some cool little illustrations here for that. Here's argon. Now, if you look at argon on the periodic table, it's got 18 electrons. You count it up, you got 18 electrons there. I'm going to cycle through a bunch of little PowerPoint slides where the little electrons are moving around. Notice that random electrons moving around all the time. Now, every once in a while, you're going to notice that suddenly we have this weird, interesting congregation of electrons on one particular side of an atom. Okay, well, this is just due to random chance. Flip a coin, you might end up with an electron there, the other place, and they just happen to end up in the same place randomly. Okay, and it might be the same thing as if you were, in a room with a bunch of people and you guys all kind of congregated in one area of the room. Although that necessarily wouldn't be random. This is random. All right, so you can see. Just keeps moving around. They just keep ending up congregated in one area. Keep moving around, congregated in one area. Keep moving around, congregated in one area, right? So they just keep congregating every once in a while. Now, every time they congregate, that means that there's uneven distribution of charge. That means there's more negatives over here than there are positives. And that's why we use a little symbol here to demonstrate that this is a slightly negative area of the atom, and this is a slightly positive area of the atom. Okay, this is called a dipole, and this is an induced dipole, but it's induced by randomness. Now, from this, another argon atom that might be nearby might have its electrons moved around, and so it suddenly becomes a dipole from the first dipole. Now this is moved around, boom. Now I've got congregation here, and so now my negative charge is on this side, and my positive charge is on that side. So the negative and positive charge just keeps moving around. Now it's over here, okay? And you'll notice I use this little symbol to demonstrate a partial charge. This is not a positive and a minus. It is a little symbol with a minus and a positive, okay? And that's just to indicate a partial charge. So now let's look at this in terms of multiple argon atoms. They're all next to each other. Notice how this little argon atom has a little congregation there. What happens is that little congregation of electrons is negative, and if that's the one that started randomly becoming negative there, the argon atom that's next to it is suddenly going to be like, whoa, my electrons don't want to be next to it, and so it pushes its electrons over in this direction. So now this is an induced dipole. I've got some negative here, which is going to induce a positive here. Okay, so negative suddenly induces positive, which induces negative, which is going to induce positive, which is going to induce negative. Okay, I mean, and it just kind of, it's like a chain reaction in a sense, right? It just kind of, of course, the electrons are still moving around, so that can change. But for a brief moment in time, you end up with these attractions between positives and negatives of different argon atoms. It's an induced dipole. Now, you can't quite read that, but this is a boiling point for argon gas of negative 185 degrees Celsius, or 87 Kelvin, okay? Negative 185 degrees Celsius, very, very, very low melting point. But what would it be if I went to krypton, which is lower, or xenon, which is lower than that, okay? Would the boiling point go up, or would it go down? Is there going to be more attraction or less attraction? Remember, I said that if you have more electrons, you're going to have a bigger induced dipole because you've got a bigger charge. So as I go down the periodic table from argon to krypton, my boiling point should go higher because there's more attraction. It's going to take more energy to break it apart. And that's what we're talking about here. This is a fun one. If we look at iodine, what's the difference? They're both halogens. Iodine and fluorine, both halogens. One of them is a solid at room temperature. The other is a gas at room temperature. Why? Well, because iodine has a lot more electrons, 53 electrons compared to 9. So both of them are going to have random distributions of electrons. Both of them are going to have London dispersion forces, induced dipole, induced dipole. But because this one has a 53 electrons that might get thrown around, it's going to have a much bigger negative charge than fluorine will be having. And so this is a negligible intermolecular attraction, whereas this is significant. So this gets to be a solid because they're attracted to each other more. That's an intermolecular force, right? Iodine is an I2 molecule. Fluorine's an F2 molecule. These guys are not attracted, even though the electrons are moving around. But these guys, woo, got a little attracted. And so we're going to induce dipole, positive, negative, boom, together. Pretty cool, right? All right, so that's kind of the idea here. More electrons, bigger charge. Smaller electrons, smaller charge. And so you're going to get these infrequent momentary dipoles with fluorine. But iodine, you're going to get attraction. It's going to be a solid. Okay, so I'm going to skip through that one. This is another thing to think about, which is kind of cool because you're like, well, what does this have to do with everyday life? Something like Teflon, which was accidentally discovered, by the way. But Teflon has all these fluorines surrounding all these carbons. And so they're pulling equally. It's a nonpolar molecule. And what it means is that the food is not going to stick to this because there's not much of an attraction there. There's only thing you have there, because it's a nonpolar molecule, is an induced dipole of London dispersion force, which is not much. Now, I don't know if you guys have realized, but Teflon is now considered carcinogenic. Back when I was a kid, they didn't talk about that. Teflon was a brand new, yay, cool thing. But Teflon is actually those little chips on the bottom of your pan. If it starts to kind of come apart, stop using that pan, because those little chips go inside your body and it's supposed to be a carcinogen, and they don't want you to use that stuff anymore. So they don't even make Teflon pans anymore, I don't think. They've got different technologies that someday we might discover might be hurting us again, but who knows. All right, so we now know that temporary dipoles are more significant for larger atoms, but they're also significant for larger molecules. And here's something cool. When you think about the gasoline, octane, okay, that's a big primary component of gasoline, versus methane. It's kind of like a little Velcro strip. And if I've got a whole bunch of tiny little pieces of Velcro all stuck together, like if you had those little Velcro, if you had two little hooks of Velcro, they're just like that would be so easy to pull apart, right? But if you get a whole bunch of Velcro pieces and you try to rip them apart, they're not going to be easy to pull apart, right? You got to pull them apart from one end and just get a couple at a time. That's what's happening with things like octane. And that's why octane is going to be a liquid at room temperature and have a higher boiling point than methane, which is natural gas, right? This is the stuff that comes through our little gas spigots here. It's the stuff that you would have at home going and supplying your gas furnace. Methane doesn't have as many attractions, but octane has lots of attractions. Liquid at room temperature, gas at room temperature. Pretty cool, right? All right. So this is our second type of force. That was all London dispersion forces. This is way cool stuff to talk about. Dipole-dipole forces. Remember, a dipole is basically two poles, okay? You've got two charges, a positive and negative charge, right? And so this is going to happen when you have polar molecules. And you're going to have the positive and negative side, and so you're going to have an attraction that occurs there. And this is a much stronger force than LDF, and this is basically like what you would have with water. Okay, so when we talk about water, why does water stick with water? Okay, it's a polar molecule. Oil is not a polar molecule, it's a nonpolar molecule. These guys do not interact. These guys are attracted to each other, and so they hold on to each other, but the oil is not attracted to the water because it's nonpolar, and so it doesn't bond. And so when you mix it together, then it still separates out because they are not attracted to each other, okay? So dipole-dipole, water, biggest example there. You're going to use water for your dipole-dipole all the time. But water actually has a specific type of dipole-dipole, which is called a hydrogen bond. Now, a hydrogen bond has to do with the connection between hydrogen and very particular other atoms. Okay, so it's a special super strong type of intermolecular force. You can type in intermolecular there, and it's going to be a connection between nitrogen, oxygen, and fluorine. Okay, with a hydrogen. Now, they've got to be connected from one atom to another atom. Okay, so basically, if you were dealing with water, then what would you have? You'd have the oxygen, right? And you'd have two of the hydrogen atoms attached to that. Okay, and it would be one water connected with another water. Now, I've got a molecule of water, right? An ice crystal, which I've shown you before. But this ice crystal has got all of these white spaces in between. Those white spaces are the hydrogen bonds. Now remember, we're using the word bond here very loosely because this is not specifically supposed to be considered a bond. Okay, we call it a hydrogen bond, but it's not a chemical bond. It's not as strong as a chemical bond. It's an intermolecular attraction, intermolecular force, but it's not technically a bond. And that's why when you break these hydrogen bonds, you're going to melt it and change phases, but you're not going to actually change the chemical. Now, some chemicals you could change as you start to break their hydrogen bonds. You might actually break some of their chemical bonds as well. But in this case, with water, as you slowly heat it up, you're going to break some of those hydrogen bonds, and it's still going to be water because you're only breaking the intermolecular attractions between those different water molecules. All right, so what is it? It's a hydrogen atom bonded to an atom with a high electronegativity, and basically it's the attraction to that unshared pair of electrons. So here on this particular example, you can see like my oxygen here has an unshared pair of electron because it's not bonded to a hydrogen, right? Or a hydrogen. This is an unshared pair, that's an unshared pair. And so this unshared pair of electrons is attracted to the proton here of this hydrogen. And that hydrogen, its electron is mostly right all the way over by this oxygen because oxygen is way more electronegative. So this is a positive part of the molecule. This is a negative part of the molecule. So the negative here is attracted to the positive here, and that's what you can see. And you form these hexagons where every positive is connected with another negative, which is kind of neat. Let's see how that works out. All right, so that's hydrogen bonding. And you can kind of see how that hydrogen bonding worked. I showed you an even better molecule of it just there. How do I determine the dominant intermolecular force in a molecule? Well, I've got to draw the Lewis structure, figure out its shape, determine its polarity. If it's nonpolar, then the only intermolecular force I have involved is LDF, Laminar dispersion force. If it's polar, but there's no hydrogens connected to nitrogen, oxygens, or fluorines, then it's a dipole-dipole, which is strong, but it's not as strong as hydrogen. This is the strongest one. And this would have a hydrogen connected to a nitrogen, oxygen, and a fluorine, and then connected and attracted to other molecules that are there. That would be hydrogen bonding. That's going to be the strongest. Now, remember, hydrogen bonding is a type of dipole-dipole. It's just a specifically strong type of dipole-dipole. And hydrogen bonding is what holds your DNA molecule together. It's cool, right? Okay, so let's determine some intermolecular forces in this molecule, NH3. First thing you got to do, right? Go ahead and pause and practice, see if you can do it yourself. And we're back. NH3, you guys have seen this one before. This is ammonia. One bond between each. It's got a lone pair of electrons, which means this is a polar molecule. Does it have a hydrogen connected to a nitrogen? It does, which means we have hydrogen bonding here. Okay, so not only is it polar with a dipole-dipole, it's a special type of dipole-dipole. It's hydrogen bonding, and that is a strong type of bond. Okay, let's look at the next one. They think their pictures are better than mine. I think mine's better. All right, yeah, yeah, we already did that. Oh, we forgot to tell you the shape. Yeah, did you figure out the shape? Trigonal pyramidal. Okay, again, you do that little line of symmetry, and it's not symmetrical, right? And yeah, hydrogen bonding, boom. And you get to try it here. HFCl2, HCl, what do you think about the intermolecular forces, and which of these would have the highest boiling point? Pause it and practice, and I'll give you the answer here in a second. And we're back. And HF, Here is our Lewis dot structure, Cl2. Here is our Lewis dot structure, HCl. Here is our Lewis dot structure. Okay, symmetry here, boom. This one is nonpolar. That one is the weakest attraction. The only force of attraction involved there would be LDF. It's a linear shape. All of these are linear shapes. But that is going to be the one that will have the lowest boiling point. Okay, so lowest because it has nonpolar attractions. HCl, definitely not symmetrical. This is polar. Electronegativity difference here versus here. This is a bigger electronegativity difference, which means that this has a stronger polar bond. And that means that this one is going to have, and besides it's got fluorine in it, remember we said oxygen, nitrogen, and fluorine as hydrogen bonding. This one's going to have hydrogen bonding in it. Strongest type of bonding. That one is going to be the highest. This was the lowest. Wow, that was a funny looking S. This is going to have the highest boiling point. And then this one is going to be just a dipole-dipole because this does not have oxygen, nitrogen, or fluorine attached to the hydrogen. So this is going to be a dipole-dipole bond. And that's going to have a middle. It fits in the middle there. Middle boiling point. Cool? Did you get it right? I bet you did because you're awesome like that. All right. Well, that is where we are going to stop and show you. Yeah, that's going to be the end of that one. However, we need to go back and see if we met our objectives, right? Hang on one second. Got to get back to my objectives. And objectives. Did we meet our objectives? Do we know what we set out to know? So important to find out. Ha-ha! Okay. Can we now use molecular shape and electronegativity to predict molecular polarity? Yeah. Can we articulate the difference between intermolecular attractions and interatomic forces? Yeah, one of them is an attraction, the other is a bond, right? 3 types, dipole-dipole London dispersion, hydrogen bonds, and IMFs. How do they affect the boiling melting points? Okay, the lowest or least attractive IMF, London dispersion force, is going to have the lowest boiling point, right? The biggest, strongest intermolecular force, hydrogen bonding, is going to have a higher boiling point, things like that, right? Okay. Can you explain the influence of bond polarity and molecular shape and polarity of molecule? Yeah, bond polarity is going to affect the polarity of the molecule as long as it's not symmetrical. Because if you have polar bonds, like here in methane, remember, those are 4 polar bonds because carbon and hydrogen don't have the same electronegativity. These 4 polar bonds still result in a non-polar molecule because of symmetry, right? So bond polarity does affect it, right? But you have to look at whether or not it's symmetrical, whether it passes that symmetry test first. And then, given the formula for a molecule, you can draw its Lewis structure, predict its shape, determine whether or not it's polar. Man, you guys are getting to do some cool stuff now. Given a molecular formula, you can predict the type of intermolecular forces it will have. Yeah, okay. And then we just practice some of those right at the very end there. Given formulas for multiple molecules, you can now put them in orders of increasing boiling points. Yeah, you did that too. You're amazing. You know why else you're amazing? Because you are practicing being kind to other people, and I appreciate you guys doing that. Hey, it's my message over and over again because I just want to see this world get to be a better place, and you are a part of the reason that this world will become better because you are going to continue to practice kindness and make other people know how important they are in this world. Share the love today, all right? God bless you. You have an awesome day. Thanks for listening.